better. I'm going to start today by saying that we are here to learn, and I'm excited about today's stuff. A lot of today's stuff feels like a puzzle. So if you like logic puzzles and that sort of thing, and who doesn't really, I think you'll really enjoy today's lesson on linear transformations. Before we get to our lesson, I do want to talk to you about the stuff that I promised to talk about last time. So first of all, I have decided that we'll just have your test next Thursday. I can't push it back because the next Tuesday is a wellness day, and I don't want to do that to you. And I'm also worried that if I keep pushing it back, then it will pile up with other tests. So we will plan to have a test in class on Thursday. It will be a pencil and paper test. We will be on Zoom, and we'll just be on Zoom so that if you have questions, or if I, made a mistake and need to announce something to the class, that sort of thing, then I can handle those sorts of things on the spot. So we'll have a test next Thursday. Tuesday's class is going to be a review day. So what that means is you bring questions to me, and I will answer them. So if nobody has any questions, then we'll get out of here real early. So I urge you to go and find some really good questions to ask me, and we can go over stuff as a class, okay? So I have posted the test that I gave last time that I taught this, test 1. So it is now posted to Moodle, and the key to that test is posted to Moodle as well. It covered the same material. It was also an 80-minute test, just like this one's going to be. So it's a really good opportunity to study. If it were me, if I were preparing for this test, what I would do is I would take the test and put myself in a real test situation, not look at my book, not look at my notes, sort of time myself, make sure I can do it in 80 minutes, take the test, see how it goes, compare it to the key, and that will be sort of that would be a self-assessment, sort of, how did I do? What do I need to study more? What do I need to focus on? That sort of thing. So that's the way that I would use that test. There's also a review, and the review of the test 1 has a lot of challenge problems, a lot of really great problems in there. It also encourages you to link different ideas, which is a big part of what linear algebra is. So, so definitely take a look at that review. Again, that review is posted to Moodle as well. I'm trying to think what else you would want to know. What else do you want to know about this test? I'm getting my tea here. I'm a dork. Any other questions? Yeah, go ahead, Emery.
Expect to see the same type of questions on this test as would have been on that practice test? Yeah, like similar types of questions, just obviously like different numbers and stuff.
That's a great question. So I'm not going to reskin that test, if you know the term reskin. So it's not going to be the same questions with different numbers. It's going to be different questions, but you can get a really good sense of the types of questions that I might ask. Does that help, Emery? Yeah. So the reason I don't do a reskin of a test is because I don't want you to memorize how to do problems 4, 5, and 6. What I want you to do is to understand linear algebra. And I think a good assessment of that means that I need to change the questions to something sort of different. So you can get a good sense of the types of questions, although you should expect that it's not going to be exactly the same questions with different numbers. Yep. So other questions about that test? Okay, so the other thing that I wanted to say is at the end of that test, I'll ask each of you to scan your test and email it to me. You should probably use something like Genius Scan for your phone. Probably most of you have used that before, but Genius Scan is an app for your smartphone that allows you to take pictures of your work and save it as a PDF. And then you can share it directly with me. What we're going to do is we're going to have a sort of a trial run on Tuesday. So on Tuesday, we will have your next vocab quiz. It will be a pencil and paper affair. I'll email it to you when it's time. We'll have about 10 minutes to do it, which I think should be plenty of time. And when you get done with that, you will scan it using Genius Scan and email it to me. It is important that those be emailed to me right at the end of that time. What I don't want to have happen is a person sort of, keep that test for a couple more hours or whatever, because I want to make sure that we all have the same amount of time to do it. So it will be very important before you leave to go ahead and scan that and make sure it's legible, make sure that I can actually read it. So what we'll do is we'll have a trial run on Tuesday and hopefully get any kinks worked out on Tuesday for that with that quiz. Does that make sense? So expect that vocab quiz on Tuesday. The vocabulary for the section that we're doing today is not posted yet, but it will be soon. Okay. And I should also say that test 1, the coverage is posted to Moodle, but it's the sections that we've covered, including the thing that we're doing today. So the last section that we're doing today is section 3.1 on linear transformations, and that'll be the last section of new material. Yep. I know you got more questions. Give me some more questions.
For both the vocab quiz and the test, do you want us just like looking at it on our computer and then like following along and doing it on paper, or can we print it, or?
You can do either one. You can do
Okay.
either one. Yep. If you have access to a printer, go ahead and print it out because it's probably easier that way. If you don't, you can just have it on your computer open. Yep, totally. You know, for the test, it will be closed notes, closed book, closed internet. So, you know, one of the first, you know, what I'll ask you to do first is to pledge your name to indicate adherence to the honor code. And one thing that I absolutely need to mention, and I almost forgot, if you want a calculator for test, what do you have to make sure that you have done before that test?
Computation quiz.
You got to have passed your computation quiz. That's right. So if you have not passed that computation quiz, you got a week, right? And remember, you can do 1 try per day. So so definitely don't put that off, because I want, these questions are designed to be done with a calculator. So if you don't have a calculator, it's going to take you way too long, and that will be bad. And I don't want that to happen to anybody. So make sure you pass that computation quiz before Thursday. Yep. All right, I'm looking at my notes over here to see if there's anything else I need to talk about. I don't think so. So any questions before we start talking about today's material? I've made you all nervous. I'm sorry. You'll do great. You'll do great. Okay. All right. Well, let's start talking about today's material. So the first thing that I want to do is to share my screen and sorry. So I have posted today's lecture notes. It's called 5 Lin Trans. So if you go to Moodle, there's a folder called lecture notes, and it's in there. I also emailed it to you, right? So if you got it in your email, you could use that as well. Feel free to print it out or have it available on your screen. I will say that some of my other groups earlier today, you know, if some people were having trouble seeing it, one person sort of pulled it up on their device and shared their screen so that everyone could sort of follow along. So I encourage you to do that if that works for your group. If anybody who has not been able to find that, anybody who's still looking for it. All right, awesome. So the first question is about the unifying theorem. So I'm going to share my screen and show you what that unifying theorem looks like. All right, so hopefully you guys can see my screen now, yes? Okay, awesome. This is the unifying theorem version 1. Version 1 means that there's going to be a version 2 and a version 3 and other versions, right? So we're going to sort of keep adding on to this unifying theorem. This unifying theorem says, let S be this collection of vectors, A1 through AN. And notice that the vectors are in Rn. And then you take those vectors and place them as the columns of a matrix A, okay? It says the following are equivalent. Equivalent means that they're interchangeable, that they carry exactly the same information, that if one of those statements is true, then they're all true. And if one of the statements is false, then they're all false, right? They're interchangeable. They carry the same information. The thing that I want you to write in your notes is that this theorem only works if the matrix that you get is square, meaning the number of rows and the number of columns are the same. So notice that my collection of vectors has n of them. They're n vectors, right? That's the number of columns. And each of these vectors is in Rn. So that means that there are n rows, right? So the number of rows and the number of columns have to be equal in order for us to use this theorem. If the number of rows and columns are not equal, I cannot use this theorem at all, okay? Really, really important consideration, because that's one of the most common student mistakes that I see, is sort of applying this theorem to a situation in which it's not square, okay? So let's talk a little bit about why it would be true. Part A says S spans Rn. So let's think, how do I tell if vectors span Rn? What am I looking for in terms of the pivots there? Anybody?
A pivot in each row.
Pivot in each row, absolutely. So in order to span, I need a pivot in every row, exactly. So, but of course, here the number of rows is equal to the number of columns. So if there's a pivot in every row, what else could you say for this particular situation?
That there'd also be a pivot in every column.
Right, because there's exactly the same number of rows as columns. So if there's a pivot in every row, there's also a pivot in every column, and that's exactly what B says. B says S is linearly independent, which means that there's a pivot in every column, right, as we talked about last time, right? Of course, it sort of goes the other way as well. If I knew at first that it was linearly independent, meaning that there was a pivot in every column, since the number of rows and columns are the same, then I also know that there's a pivot in every row. Again, this only works if the thing is square, right? It's certainly possible to have a pivot in every row, but not a pivot in every column if things are not square, right? If things are not square, those numbers could be different, okay? Part C just says that AX equal to B has a unique solution for all B. And that also requires you to have a pivot in every row, right? A unique solution means that there's no free variables. And if there's no free variables, then there must be a pivot in every column. And again, we know that spanning and having a solution are also the same. So part C is also sort of very much about there being a pivot in every row and column, okay? Does that make sense? Any questions about this unifying theorem? Okay, really important theorem, but limited because it has to be a square matrix. Only applies if it's a square matrix, okay? If the number of rows and the number of columns are the same. All right, very good. All right, so I'm gonna stop sharing that. I'm gonna share my other screen so we can sort of take a look at the next thing. Well, I'm gonna try to stop it. There we go. There we go. All right, so give me a moment. All right, hopefully you guys can see my screen now, yes? Okay, move that out of my way too. Okay, so at the beginning of our worksheet, we're talking today about linear transformations, which are basically just functions in linear algebra, and that's the way you think about it. We do have some terminology in this section that you're probably familiar with. I just want to remind you of what these terms mean. So let's head on over here. And sort of remind you about sort of other contexts that you've probably seen this stuff in. So sorry, I didn't have enough space to write it here, so I wrote it at the end. So because I kind of write big, but this is sort of what I'm thinking of in that first bit. Okay. Also, I've already got this stuff written down, and I'm gonna kind of move through it kind of fast. However, note that I'm recording this. Okay. So if you miss anything, you can always go back and look at the recording later, okay? So no big deal if you miss any part of it. My advice to you is to focus and try to absorb what we're talking about today. Don't worry about copying it all down. You know what I mean? If you try to copy everything down, you might miss something that's important for your understanding. So instead, focus on your understanding, and then later you could sort of go back and focus on writing it down. Because again, the video will be posted, okay? So that's my advice. Again, if you feel good about writing it all down in this time, go for it. When we have functions, they map from A to B. So A is called my domain, right? And that's pretty familiar to most of us. This one here is called the codomain. That's a funky word that I did not know when I took my preliminary exam in graduate school. And one of my professors said, oh yeah, the codomain. And I said, I don't know what that is. And I felt really embarrassed. You know, this is one of those exams where you're at a blackboard and you've got 3 professors who are quizzing you on everything. And I just said, I don't know what codomain is. And he described it and I was like, oh, it's the one that the arrow points at. And he said, yes. I was like, ah, man, why didn't you just say that? And once I knew that it was the one that the arrow pointed at, I sort of moved on. I will say that mistake, embarrassing as it was, I've never forgotten what codomain is, and I will never forget that. because it's sort of permanently into my brain. So codomain is the one that's pointed at. The way that I think of these things are the domain are your inputs, and the codomain is the set of possible outputs. Okay, it's where possible outputs are. The range is the set of actual outputs. Okay, so the range is those things that actually occur as an output, whereas the codomain is the things that could be outputs. Okay, and I'm going to give you an example here because it's kind of abstract without examples. So one-to-one is probably something you're familiar with. I think of one-to-one as being no collisions, meaning every input goes to a different output. Okay, I don't ever have any collisions, right? I don't ever have a situation in which I've got an input over here and an input over there, and they both map to the same output, right? So that never happens. I don't ever have sort of two different inputs mapping to the same output. Okay, and we also have the idea of onto. Onto means every possible output is an actual output, right? Meaning that the range fills up all of the codomain. Right, so the range is the set of actual outputs. The codomain is the set of possible outputs. So if the range fills up the entire codomain, we say that the function is onto. Okay, so let me give you an example. Here is a function from R to R. It's f of x equal to x squared. It's my good old parabola because I can sort of picture that pretty well. This function is not one-to-one because not every input goes to a different output. In particular, -1 and 1, when I square both of those things, they're both sent to the number +1, right? So I've got -1 and 1 both colliding at the same output. Does that make sense? So this function is not one-to-one. Okay, it doesn't pass the horizontal line test. Okay, and this function is also not onto. So onto would mean that every possible output is an actual output. But this function does not reach all possible outputs because the set of possible outputs is R, all real numbers. But this function never goes to the negative numbers, right? I can never square a number and get -2 as an answer. Okay, I can never square a number and get -5 as an answer. So it's not onto. The set of the range, the set of actual outputs, is just the set of positive numbers, whereas the codomain, the set of possible outputs, is all of the real numbers, right? And since the range doesn't fill up all of the codomain, this is not an onto function, right? So that was kind of fast. Again, I think that you are hopefully familiar with some of this stuff from like calculus and that sort of thing. You have any questions sort of about what these intuitively mean?
When we're looking at that top function part where you have the domain and the codomain,
Yes.
are those kind of like given to you? Like if you have, like for that one, both of them are all reals.
Yes.
Are those like given to you in a problem, or do those have significance? Because if you're looking at it and you see the codomain is all reals, but you know in your mind that it'll only be positive numbers, like why is it that that number would be all reals?
Yeah, so that's a good question. In order to specify a function, you have to specify both the domain and the codomain. So that's always given to you. It's always handed to you. The question as to why you wouldn't just know, why wouldn't you say that the codomain is just all positive real numbers, right? Or all non-negative real numbers? You could, but then that forces you, every time that you write down a rule, you can't write down the rule until you know exactly what the range is, right? And that's more work than mathematicians want to do. So it's easier for mathematicians to just say, this is sort of roughly where the outputs are going to be. And if we need to compute the range, we will, but we don't need to specify that at the beginning. Again, because mathematicians are lazy. Does that make sense, Emery? And I will say that for some functions, it's very, very hard to understand exactly what the range is. Like that might be a problem that no mathematician has ever solved. And that doesn't mean that we want to disregard that as a function, right? So we want to keep things as broad and general as possible. It's a great question. Other questions? All right, very good. So I'm going back up here to the top. Okay, so we've done sort of number 2. Number 3 is linear transformations. Linear transformations are the functions that we'll be dealing with in this class. Number 3 is a definition of linear transformation. You will need those 2 bulleted things in order to do all of what comes next. So look at those 2 bulleted things carefully when you get into your groups. And these are puzzles. So work with your team to see if you can figure out these puzzles. If you need help, of course, ask for help. So I'm going to stop sharing, and I'm going to put you into your breakout rooms. So give me just a moment as I set those up. Let's see. There's no real fast way to do this, sadly. There's no fast way that I know to do it. All right, 2 rooms done. All right, so I also want to tell you what your roles are for today. So let's see. So Luke, last time you were manager, yes, Luke?
Yes.
Awesome. So Fields, today you will be manager. Emery, you will be reader, and Luke, you will be spokesperson. Okay, in the second group, Meredith, you're going to be manager today. Mark, you are going to be reader, and Rachel, you will be spokesperson. Today in the third group, Landon, you will be manager. Eliza, reader. Jeet will be spokesperson. And finally, Zach will be manager. Drew will be reader, and Bella will be spokesperson. All right. Any questions about what your role is? All right. I'm going to open these up now. Hopefully this will take about 20 minutes, 15 or 20 minutes. That's our goal anyway. If you get stuck, don't hesitate to ask for help, and I'll come around and check on you guys in a few minutes. All right, so you should see the opening up now. So we'll get started again once we get everybody back. And I know that not everyone finished, and that's totally okay. But we will work through some of the ones that you guys didn't get a chance to get to. I think we're still waiting on a couple. All right, I think we're all back, and I am recording again as well, and hopefully you can see my screen. Yes, can you guys see my screen? Okay, perfect. So I want to take a look at some of these and present some answers, make sure that we feel pretty good about them, make sure we got the same sort of things. I don't feel that we need to go through all of them, because I think if you got some of the later ones, that tells me that you must have gotten the other ones as well, right? You must feel good about them. I'm actually going to start with, let's see, I'm going to start with part C here. And let's see, Bella, were you spokesperson for your group?
Yes.
Tell me what you guys got for part C.
We got 1, 4.
1, 4. Is that what other groups got? Okay, awesome. Sounds good. Good. And how about, let's see, Eliza, were you spokesperson for your group?
No, Jeet was.
Oh, Jeet was. Sorry, Jeet, spokesperson. Would you? Yeah. Sorry, I miscounted. So Jeet, tell me what you guys got for part D here.
Got 0, 0.
How'd you get 0, 0? Can you sort of take me through your reasoning there?
We did T of 0 times U, and then we took out the 0 and then multiplied it by T of U.
Good. Let me ask, did it matter what T of U actually was equal to in order to know what T of 0, 0 is?
No.
Doesn't matter at all. In fact, your group just proved that 0, 0 always has to go to 0, 0, right? The vector 0 is always sent to the vector 0 by a linear transformation because of that sort of second property. Good. So any questions about part D? Great explanation, Jeet. Thank you. So let's see. Whoa, that's not what I meant to do. Let's try again. There's a weird line there. Makes me happy. Let's see. Jeet, I'm going to ask you this one too. What did you guys get for part E?
We got -3, -2.
-3, -2. Is that what other groups got? I'm seeing some nodding. Great. Awesome. So it seems like we're all on the same page. It's fantastic. Let's see. So Rachel, were you spokesperson for your group?
Yes.
Awesome. So Rachel, tell me what you guys got for part F. Sorry, and I'm going to ask you in a couple different places. You guys first wrote -3, 5 as a linear combination, right? What was the linear combination that you got?
-8.
Times u?
Yes.
Okay, and then what's the next one?
5 times b.
Good. So you got something like -3, 5 is equal to -8 times u plus 5 times c. Is that what other groups got? Okay, good. I see some nods. Is that what other groups got? Yes. Okay. So and then Rachel, what did you get after that? So after that you broke it apart and you did some work. What was your final answer for t of -3, 5? What'd you get?
Oh, I just did it all in like one thing.
All in one thing. What do you mean by that?
Oh, never mind. Sorry. -21 over -19. I'm sorry.
No. You're good. You're good. So I mean, I was asking. Sorry, I was sort of skipping to the end there. Sorry, my bad. So you guys got -21 over -19 after you sort of used the properties and you just sort of computed it. So Fields, you guys got the same thing. Is that right? Other groups got the same thing too. We all feel good about it. Any questions about this one? All right, great. So we're moving right along. So I'm going to look at part G and H, and I'm going to ask Luke, were you spokesperson for your group?
Yes.
Awesome. What did you guys do for part G? So for part G, I presume that you first wrote x1, x2 as a linear combination. What did you write how did you write it as a linear combination?
Well, first we did x1 times 1, 0 plus x2 times 0, 1, and then we went that and made it x1 times the 2, 3 vector plus x2 times the -3, -2 vector.
Good. So when you did like x1, x2, you sort of did it this way. Oops. Yeah, you sort of break it apart that way using the properties.
Yes.
Yeah, and then when you finished, what was your sort of final answer after you sort of computed all this? You sort of combined it. What did you get at the end of that?
2x1 minus 3x2, and then 3x1 minus 2x2.
Good. Did any other group get this far? Okay, so I see at least one nod. So Drew, and did you guys get the same thing? Okay, cool. So I'm just going to sort of highlight this. This thing right here is t of u, which we know what is, right? And this thing is t of 0, 1, which we computed in part something or other. So using those two things that we already computed, we can combine them and multiply by x1, multiply by x2, then combine them. Once we do that, we get something like this, right? 2x1 minus 3x2 in the first spot, 3x1 minus 2x2 in the second spot. Good. So I'm going to pause here and ask if there are any questions about how we got there. I have had students ask, why 1, 0, and 0, 1? And that's a really good question. Why 1, 0, and 0, 1? 1, 0, and 0, 1 make this thing right. Whoops, sorry. 1, 0, and 0, 1 make this calculation really easy. Okay, it just makes it just super, super easy. And so that's often my go-to. If I'm thinking about what vectors to use, I might think 1, 0, and 0, 1, just because it makes it really easy to write a general linear combination. Okay, I'll just say that. So Luke, let me ask you this too. You guys rewrote this. You guys wrote a matrix A. How did you do that? What was your matrix A? What did your matrix A look like?
We had, I guess the top row is 2, 3, and then the bottom row is -3, -2, and then multiplied by the x1, x2 vector.
Say it again. Your first row was what?
2, 3.
2, 3.
Or first, yeah, first row. Yeah, and then -3, -2.
Oh, I think I screwed up, didn't I? So I think my previous highlighted thing is probably incorrect, maybe, or did I get it wrong? So let me ask this. Luke, the thing that I highlighted there in the last line, the thing in pink, is that what you guys got?
Yeah, we weren't really sure whether to switch to 3 and -3 because of multiplying by the x1, x2 vector.
Yeah.
So we weren't really sure about that.
It's a good question. So I'm gonna go back. I think that's a great question. So that pink highlighted thing, I'm gonna work with that a little bit. I'm gonna write it this way. I'm gonna write it as 2x1 3x1 plus negative 3x2 negative 2x2, and this is sort of going back, you know, or an earlier stuff, but that's okay. Right? So I've just sort of taken out my x1 and my x2 stuff. When I've written it this way, now it is written in the form of a linear combination. So since it's written in form of a linear combination, I can immediately read off my matrix. Right? So this last thing here, that has rewritten my T of x as a matrix A times a vector of unknowns. That matrix there is the one that I would go with, right? Because matrix multiplication is defined as a linear combination of the columns of A with the weights in that vector, right? So I think that you guys may have swapped it, Luke. I think your group may have sort of swapped the rows and the columns, which is totally okay. But generally, you know, matrix multiplication is a linear combination of the columns. So I think that this is the one that I would get. Right. So I know that there's some questions about that last part, about part H. So who's got a question that we can talk through? All right. I'm going to say again, this thing right here, that thing that I've circled is A. That's my whoops. Oh yeah, I see. Let's do a different color maybe. All right, so that matrix right there is my A. That should be for H. All right, nice job. That was tricky. That was hard stuff. Hopefully you have learned a little bit about sort of what a linear transformation is and maybe how to use those properties to be able to actually do something with a linear transformation. I will say that number 5 is important. Every linear transformation can be written as a matrix A times a vector. It can always be written that way. Generally speaking, when we give a linear transformation, I just give you the matrix A, okay? That's generally what we do. Because, and you use this same process to sort of figure out what that matrix is each time, okay? So I'll just sort of say that. So let's see. I was trying to think if we put you in groups or not. I worry that if we go to groups, then we're not going to have time to present. So we've got about 15 minutes or so left in class. So what I want to do is to work through number 6 and 7 together as a class. Okay. So, but by together, I mean, I really want you guys to respond and tell me what you're thinking. Okay. Instead of me just telling you stuff. We can't learn this stuff unless we make connections on our own. It cannot be learned by me opening your brain and pouring the knowledge in, right? You got to do some work on your end to make sure that the knowledge goes in. So I want you actively engaged in this part. I'm going to look at the definition here, number 6. Number 6 says, if T is a linear transformation, then we say that T is 1-to-1 if for every vector W in Rn, there exists at most one vector U such that T of U is equal to W. That means that different inputs have to go to different outputs, okay? Another way to say this is if T of U is equal to T of V, meaning two outputs are the same, then that implies U is equal to V, which means that the two inputs have to be the same, right? So this part right here means that if I have two equal outputs, then in fact they must have come from the same input, right? That the two inputs must have been the same as well. Okay, so we want to understand how to be able to tell whether a matrix is whether a linear transformation is 1-to-1 or not. And again, the trick is how many different inputs go to a possible output. So we're looking at number 7. So basically, number 7 says, this thing here says that if I start with a vector U, in order to compute what the answer is, I take the matrix A and I multiply it by that vector U. Okay, that's the way that I compute things, right? So right? And again, for us, it's going to be this one, right? Like that. Okay. So we're sort of looking, is it possible for multiple inputs to go to the same output? So I want to look at part A here. The easiest vector that I might investigate is the 0 vector. So I might ask how many vectors are sent to 0 by t, right? Or how many solutions does that have? So let's rewrite that in a different form. How many solutions does t of x is equal to 0 have? Okay. All right. I'm just sort of rewriting things in different forms. Okay. So I want to point out that I'm not asking what the solutions are. I'm only asking how many solutions are there. How many solutions do I have to this this system that I have written down, and how do you know?
Would it be 2 because you have an x1 and an x2?
Good. So I mean, I agree mostly. You do know what x1 is, and you do know what x2 is. But I will say that if you have one value for x1 and one value for x2, really that just gives you one answer.
Oh, yeah, true.
Yeah, because your answer is a vector, one single vector, one sort of vector, right? So yeah, I agree. There should only be one value. The only solution is 0, 0, right? I mean, another way to ask, is there more than one solution? What am I looking for in terms of the variables if I'm looking for whether there's one solution or multiple solutions? What would it mean if I had infinitely many solutions? What would that look like?
The bottom row zeros.
Okay, that's a good way to think about it. It's not necessarily the bottom row, though. I agree. In this situation, if I had the bottom row be zeros, I think it would be infinitely many solutions, totally. I think usually if I have infinitely many solutions, I have a parameter, yes? I have a parameter. What does that tell me about the variables if I've got a parameter?
They include.
It's okay. So we'll work through it in just a moment. Let me. I'm getting ahead of myself anyway. So sorry. I'm gonna work through this carefully. Meredith, you said that there's exactly one solution to this. I agree.
Right.
Exactly one solution. If I was unsure, I would use an augmented matrix, hit the button in my calculator, and it would spit out that x1 is equal to 0, x2 is equal to 0, right? x1, x2 is equal to 0, 0. Whoops, 0, 0. Right, there's exactly one solution. Right. The next one sort of asked me to maybe rewrite this differently. Hopefully my answer included something about positions of pivots. So maybe we should give an alternate explanation that includes information about the position of pivots. So let me write this. Notice, every variable is a leading variable. So there is no free parameter. This means only one solution, right? Because there's no free parameter. Free parameter means that there's infinitely many solutions. If there's no parameter, free parameter, there's only one solution, right? So how do we know that everyone is a leading variable? There is a pivot in each column, right? So the pivot in every column means that there's no free variables. Does that make sense? Right. Any questions? All right. It says, now think about the more general equation, t of x is equal to b. right? Not just 0, but B. This equation may have 0, 1, or infinitely many solutions depending upon the matrix A and the vector B. If the equation has infinitely many solutions for some B, then would that mean that T is 1-to-1 or not 1-to-1? Explain. What do we think? If there's infinitely many solutions for one B, does it mean that it's 1-to-1 or not 1-to-1?
Not 1-to-1.
Why do you say not 1-to-1, Emery?
I mean, I guess just because if there are infinitely many solutions, then odds are that at some point there would be like a collision.
Yeah, so in fact, if there are two solutions to something, that two solutions mean that there are two inputs mapping to the same output. So in fact, if there's infinitely many solutions, that means that there are infinitely many things all mapping to the same thing, right? A solution is an input that maps to that output. So infinitely many solutions says multiple inputs for one output, not 1-to-1. Right? So if there's infinitely many solutions, we know that it cannot be 1-to-1. A solution is an input, and the B is your output. Okay, so fine. So I'm going to leave that here, maybe. So finally, it says fill in the blank with either the word row or the word column as appropriate. The linear transformation T is 1-to-1 if and only if the echelon form of the matrix for T has a pivot position in every. What should I write there? How do I tell if there's infinitely many solutions or not?
It'd be column.
Definitely column. All right, and let's write that down. T is 1-to-1 if T of X is equal to B has only one solution, not infinitely many solutions. This would mean no free parameters, no free variables. So every variable is leading. So pivot, I'm running out of space, in every column. Okay. So 1-to-1 means that there's only one solution. That's exactly what 1-to-1 means. That means that there can be no free variables. And I look for free variables by looking at pivots in columns. That's what I do. That's kind of a lot to absorb. So any questions about that? So the upshot is we've been thinking about this idea of 1-to-1 for linear transformations, and we've just linked it to something else that we are very familiar with, and that is that the linear transformation is 1-to-1 if and only if there's a pivot position in every column. Now, that is connected to another fundamental concept that we have studied. What does it mean what is another way of understanding a pivot in every column? What's another concept that's very closely related to that?
The span of where something can go.
You're very close. Span, though, is related to pivot in every row. So span is related to pivot in every row. So if it's not span, what's it going to be? It's the other one. It's linear independence. So pivot in every column is the same thing as the vectors being linearly independent. So I'm just going to note that there's this cluster of ideas. Let's do a different color maybe. Pivot in each column. Vectors, or let's say, let's go back. Let's say columns. Nope. Columns linearly independent. And the idea of linear transformation is 1, 2, 1. Those things all go together. Those are all sort of rejiggering the same idea, repackaging the same idea. Different words, same idea. They're all related to a pivot in every column. I would say that if you have memorized those ideas and those ideas are connected, that's good. Better would be if you understand how they're connected. Okay, so that's our ultimate goal. Our ultimate goal is to really understand how these things are connected and be able to trace through why those ideas are connected. If you're not there right now, that's totally okay. We will get there. Okay. So we're almost out of time, so I want to stop here. Before I do, one thing that we have not looked at yet is the idea of onto. Okay. So onto is a very different idea. I will say though that we recognize that one-to-one is connected to the idea of a pivot in every column. Anybody want to make any predictions about what onto is related to?
A pivot in every row?
Pivot in every row, it's a good guess. And pivot in every row is also connected to what other concept that we have talked about? Rachel, this is the one you were thinking of before, right? This is that the vectors span all of Rn, right? So we see that one-to-one and onto are completely new concepts, but really they're just the same as the ones we've already studied. Okay, and we'll come back to that next time. So I will say that it looks like we have a lot left to do. We don't. Part B, we're going to move through Part B pretty quickly at the beginning of next time, and we're going to look at this idea of onto pretty quickly as well. Okay, so at the beginning of next class, we will have a vocabulary quiz, and then we're going to finish up this material, and then we're going to have our review. I will say number 10 is some great challenge questions there. Great practice for a test. We do have 3 minutes left. Do you have any questions about the material we've covered today? What's happening on next Tuesday? What's happening next Thursday? All right, awesome. I will say, I understand that this can feel overwhelming, and it's only overwhelming because it's very new to you, but you've done the hard work in today's class in grappling with some hard issues. And since we've done the hard work of grappling with those issues now, you will find, I promise, that it gets easier when you go back and do your homework and you do the reading and you start studying, okay? So we've already, the hardest, most challenging, most frustrating part is the first part where it's hard to know, you know what I mean? Like it's just hard to get in your brain. We've done that work already. It's gonna get easier from here, I promise. So I look forward to seeing you all on Tuesday. I will post a link to this video so you can take a look at anything you missed. Remember, I do not have office hours today, but I do have office hours tomorrow from 1 to 2. So I want everyone to have a great weekend, and I will see you next week or Friday.
Thank you.
Thank you.
Thank you.
Mm-hmm.